We'll get started here in about a couple more minutes with the first seminar of the day at the Dairy Forage seminar stage. So be making your way over to the stage. We'll get started here at the top of the hour. All right, we'll go ahead and get started this morning. I'll begin with a real quick introduction of myself, and then we'll turn it over to our speaker. My name is Dennis Hancock. I get to be the Center Director for the U.S. Dairy Forage Research Center based here in Madison, but we also have a research farm in Prairie du Sac and a research facility in Marshfield as well. So really excited to be here this morning to introduce our last speaker of the week for our seminar series. We saved the best for last, Wayne. We really appreciate you coming down from our Marshfield unit to talk about some of your experiences with baled silage and some additional considerations here on making good quality baleage. So with that, Wayne, I'll turn it over to you.
Okay, everybody here. It's good to be with you all this morning. I really appreciate the opportunity to be here. And we're going to talk this morning about some of the work we've been doing primarily in Marshfield with baled silages. And I want to start out by just mentioning that I'm going to dispense with the normal extension-related how-to slides. And these are going to be more, after a brief set of introductory slides, just some specific things that we've worked on that address common questions or problems related to baled silage. And hopefully some of these things are things you've thought about or grappled with, and if we can shed some light on some of that, that'd be a really good thing. Okay, real briefly, what is baled silage? For anyone who's not aware, this is forage that's baled conventionally. It can be with a square baler or a round baler, probably most commonly with a round baler, but I certainly wouldn't say exclusively. And then wrapped in plastic film to exclude air. Options exist for individually wrapped bales on the left, and those wrapped with an inline wrapper that you see here on the right. This mode is a little more efficient time-wise, requires a little less plastic. This type over here may be a little more flexible in terms of marketing and for some other reasons. For us personally as scientists, this is a little easier to work with because every one of those bales can then be an experimental unit in a statistical analysis, whereas that gets a bit more complicated if they're all wrapped together. So that's not your problem, that's our problem. Most principles of silage management are the same or similar between conventional bunker or bag type chopped silage and baled silages. However, the fermentation within baled silages is always restricted compared to precision chopped silages. And there's a couple different reasons for that. One is the lack of chopping action. In order for silages to ferment, you have to have the plant sugars come in contact with the lactic acid producing bacteria that are generally adhered to the outside of the plant. So in a baled silage like this, much of that has to occur by diffusion because they're usually baled in long stem form. Whereas this is chopped, and it makes it a little easier to blend the sugars with the bacteria required for fermentation. Oftentimes, almost always in fact, baled silages have a lower moisture concentration, which we'll talk about in some depth as we go along. And then baled silages often have a reduced dry matter density, but not always. As balers have improved and baler operators have improved, we are seeing dry matter densities that are very comparable to the 15 pounds of dry matter per cubic foot that's a typical threshold for good corn silage. So we'll talk a little bit about that too. Okay, just briefly, the idea when you make silage is to take plant sugars and convert them primarily into lactic acid. This is a favored acid because it's the strongest acid and it's the most capable of driving the pH down, which provides stability to the silage mass. There's two types of fermentation into lactic acid. One is homofermentative. You'll see that you take a simple sugar and produce lactate, very little else. And then there's a heterofermentative type, which has multiple pathways where, again, you take those simple sugars and you get lactate plus a whole bunch of other stuff. The Buchneri products that you may have heard about are actually a form of this type of fermentation. And what's attractive in that regard is the production of acetate, which has antimycotic properties. And it helps to facilitate extended bunk life. Okay, just real briefly, there are very, very few published examples of baled compared to precision chopped silages where the two silages are made at the same moisture concentration. If you'll notice, this study was done or published 30 years ago. It's out of Canada. They had baled and chopped alfalfa grass silage. It was relatively wet, about 61% moisture. And what we have here is a comparison of the pH decline as a function of fermentation time. And you will notice that for the chopped silage, the pH decline is much more rapid, and the final endpoint is considerably lower than it is for the baled silage. And that relates back to the conditions that I described in the previous slide. So it's important to keep in mind we are talking about a little bit different kind of fermentation. Now, another thing that we touched on earlier is that most baled silages are drier than conventionally chopped silages. That's not exclusively true, but it generally is true. And in this same dated publication, again with alfalfa grass forages, they baled these forages at a high moisture concentration, 60 to 65%, or what I would describe as an ideal moisture concentration. The normal recommendation for baled silages, according to Kevin Shinners here at the University of Wisconsin, is 45 to 55% moisture. So that's the kind of the normal target that you shoot for. You'll notice that the pH decline is much more rapid for the wetter material. Moisture does facilitate fermentation compared to the drier ideal moisture baled silages. Now, please file that away and we'll talk about that a little bit in subsequent slides. All right, what I want to do for the rest of the presentation is just talk about a couple of different questions, concerns, problems that are presented to us that we've done some research on, and just briefly talk about them within the context of what happens if this happens, whatever this is. We get all kinds of questions, and I hope this sheds some light on some of the common ones that we do get at the center. First one I want to talk about is bale cutting mechanisms within the baler. A lot of balers, and this is the one we actually have on the farm at Marshfield. I am a federal employee. That is not a recommendation or an endorsement. Please make sure you understand that. That happens to be the one that we have, okay? I like it, but I probably would like others too. But in this particular unit, we do have retractable cutting knives. They're 3 inches apart, there are 15 knives and a 4-foot wide baler, which gives you a theoretical cut of about 3 inches. And you can choose from within the cab of the tractor whether you wish to engage them or not. We do get questions about this. You may have seen this marketed where it's often said or suggested that if you use a cutting mechanism within the baler, you can get more forage in the bale. There's also an additional suggestion that because you're cutting this into coarsely, but into much smaller pieces than would be long stem, that it may improve fermentation for the reasons that we were talking about with chop compared to baled silages in previous slide. We did a project, Matt Akins and I, at Marshfield, and in most of our studies, the operator maintains about a 5.5 mile per hour ground speed, unless there's some reason specifically for them not to do that. That seems to work quite well. And in this particular experiment, we baled alfalfa at 4 different moisture concentrations, from basically low end of ideal up to quite wet. The normal goal or threshold recommendation for baled silage is that you'd like at least 10 pounds of dry matter per cubic foot. And at these different moisture concentrations, you can see that we were well ahead of that, except when you got to the really wet material, and then we fell a little bit short. But in terms of the cutting mechanism, I do want you to look at the difference between cut and uncut. And that looks like a very small difference, but it's probably statistically significant. In my experience, when you look at dry matter density, wet bale density, wet bale weight, dry weights, some of those are going to turn up statistically significant by comparison more than half the time. Now, how much? Usually it's less than 5% difference or so. It's not a huge amount, typically, at least within our studies. What I've got here on this slide, I've plotted for the same study, lactic acid as a percent of dry matter, and plotted that as a function of moisture concentration. And then on the right, the final pH of the silage as a function of moisture concentration. And in this analysis, the dark black line represents the cut material, and the hash line represents the uncut or long stem material. And you will notice that the cut material does in fact maintain a higher percentage of lactic acid, concentration of lactic acid, across virtually this whole range of moisture concentrations. Those two lines are statistically distinct. They are different. Now, in practical terms, they're not a lot different, but they are different. The same thing applies here. The cut material maintained a lower pH across this entire moisture range. Generally, that ranged from about 0.1 to 0.15 pH units. And as a result of this, I think if you have a vendor suggest to you that you can improve fermentation by using a cutting mechanism, that's probably a true statement. I wouldn't argue with them. I think that is in fact true. Now, the bigger question is that difference in pH of benefit to you? There's a lot of reasons why you might want a cutting mechanism in your baler. Principal one being facilitating the blending of baled silage into a total mixed ration or some kind of a blended feed product. But I think to pay extra money for that small difference is a bit questionable. And so I'll leave it at that. Another thing that we've done some work with, that's a very common question, is what happens if you have wrapping delays? A very common question. I've baled all the material. The person I'm renting the wrapper from has not showed up. How long do I have before this really becomes a problem? Or I've baled all the material and we get a torrential downpour and I can't get the stuff out of the field. How long do I have before my silage becomes a very compromised product? We did an experiment with this at Marshfield, and I need to set this up a bit. What we did, we had round bales of alfalfa, and we wrapped them either immediately on day 0, within a couple of hours, or after a 1, 2, or 3 day delay. So that would be up to 72 hours later. And if you'll notice in these graphs, these points are kind of clustered. This would be, immediate. These over here would probably be a 72-hour delay. There's some messiness in the middle. But all these slides are set up the same. And what I have plotted these against was the internal bale temperature at the time the bale was wrapped. So with a 72-hour delay, you can see that we had internal bale temperatures up around 150 degrees Fahrenheit. It was pretty hot. So this is water-soluble carbohydrates or sugar, which is a substrate for fermentation. And you notice we get a linear decline and a pretty substantial compromise in the amount of sugar that's available for fermentation because of the respiration that occurred by not wrapping those bales. Actually, the buffering capacity also increases, which is detrimental to fermentation. I'm not going to spend a lot of time on that. But if you look at the production of total acids, fermentation acids, you see a decline and then a kind of a plateau after you get out here at a 48 and 72 hours. Production of lactic acid declines with a wrapping delay in a linear fashion. And you'll notice that the final pH, although this is a bit messy, does tend to increase fairly substantially as a result of delayed wrapping. In terms of quality, which may be what you're really interested in, I think most of you know about heat damage protein. Extension services have been really good about educating people on that. I should point out that in that Maillard reaction, which causes proteins to be damaged and then unavailable to the animal, moisture actually functions as a catalyst in that reaction. So this is more problematic in wetter material compared to dry hay. And you see a, fairly rapid increase, particularly out here after 1 and 2 days worth of delay in unavailable protein. And for energy here measured as TDN, it's kind of a plateau between 0 and 1 day, and then it falls off fairly substantially thereafter. As a result of this study, we kind of came up with the recommendation that while bales should be wrapped as quickly as possible, and you'll see recommendations from 2 hours up to 48 hours, this particular study would suggest that damage within the first 24 hours is fairly minimal. Once you get beyond that, it becomes much more serious. Another question we sometimes get is, what about silage fermentation in extremely cold weather? And this is a pretty common situation in central Wisconsin where it can get very cold very quick and not too long from now. Some years ago, we looked at baling some fall-grown oats, and these forages were baled about the 15th of November. And we had one set of bales that was harvested at boot stage and another that was in an early heading stage of growth. These were both variety Vista. And we plotted here the internal bale temperature as a function of days from the 15th of November. And you will notice that the temperature declined very quickly and then remained below freezing in the center of those bales till about the 15th of April. This was an extremely cold winter. It was really quite brutal. And so it may be a bit of an anomaly, but that's what happened. And obviously we sampled these bales at different time intervals over that course of this. And you'll notice that up until we got out here to where this temperature actually crossed the freezing line, we basically got no fermentation whatsoever with either set, virtually none. And I can tell you when we sampled those bales, that material was just as green as it was the day we put it in there. Once temperature started to rise in the center of that bale, then we got fairly active fermentation. I didn't put the slide in here, but these plants were very, very highly sugared. We had some evidence of a yeast type of fermentation that produced a lot of ethanol. That can be a problem with really high sugared forages. And in that light, feeding them back there before they fermented probably actually would have been a good thing. But that's a separate problem, and I'm not really prepared to talk about that one today. Another problem is aerobic stability. We get questions about this. I've gotten questions from South Dakota and all over the place. The normal kind of situation where this comes up is I have bales in an inline wrapper and I want to sell them, but I'm going to have to expose them to do that. How long do I have before they deteriorate? How quickly does the purchaser have to use them? Or I have cattle 20 miles away on a pasture in the wintertime or some other type of setup, and I need to haul silage bales to those cattle, and it doesn't make sense to haul them one at a time. I want to put them on a trailer and haul a whole bunch of them, but maybe I have to expose them to do that. How long do I have before they deteriorate? Now, to set this up, I'd like to tell you that we're incredibly smart and plan everything perfectly, but in this particular case, I'd have to be honest and say that's not the case. In this particular experiment, we were all set up to do a hay project, and about 24 hours before the material would have been ready to bale as dry hay within that project, we got a freak rainstorm that deposited, I don't know off the top of my head, something on the order of about a 1/4 inch of rain. So the farm manager, Scott Foreman, gave me a call and said, "What do you want to do?" And we basically called a bit of an audible and decided, well, how about if we put propionic acid-based preservative on this material and wrap it as silage? I've had some questions about, what are the consequences of doing that? And then would go on and look at aerobic stability in these forages after we remove the plastic sometime later. So we baled these alfalfa grass forages that had been rained on at 52 or 44% moisture and stored them over winter for 242 days. And at the time we removed the plastic, you will notice that actually the application of propionic acid-based preservative at different rates, and these rates were simply applied by using the different pumps that are on the applicator associated with our baler, actually modestly suppressed fermentation to some degree. This is pretty evident here in total fermentation acids. There's some reduction in lactic acids. There's better utilization of water-soluble carbohydrates and so forth. The ideal moisture material fermented better than the dry material, which you would also expect. Okay, after 242 days, we removed all the plastic and set these bales on wooden pallets on a concrete pad and monitored the surface temperature in those bales for 11 days. And this was done in May, and the mean maximum temperature during that time period was just under 60 degrees Fahrenheit. You'll notice very quickly that the control bales that received no preservative demonstrated by increased temperature considerable evidence of aerobic deterioration. The very mild rate did exhibit some evidence of that, but it was quite different than the control. And then, quite frankly, the two larger or higher rates of application got very little heating over an 11-day period at a time when the temperature certainly would support aerobic deterioration. Now, After those 11 days, we went back and sampled the surface of those bales again. So what I've put up here is the original analysis that I showed you on the previous slide. And then after 11 days of exposure, there's a couple things I need to point out. Compared to up here, you'll notice in the control bales, there was a very large increase in pH. It's very substantial. Telltale sign of aerobic deterioration is always an elevated pH. You'll notice water-soluble carbohydrates were utilized during respiration. They're far less here than they were up here. There's a pretty large reduction in lactic acid and also in the total acids produced or available. However, you'll notice that the changes in these two higher rates were really very, very minimal. So this was very encouraging. And then we decided we'd repeat that because that's always a good idea. You don't want to get too excited about one study because there can be all kinds of things that might prove not to be true. But in this particular experiment, we used grass, meadow fescue, orchard grass, and tall fescue. These were ensiled at a relatively low moisture, just under 40%. They were stored for 84 days. And then they were exposed for 2 weeks in October. And again, the mean maximum air temperature was just under 60 degrees Fahrenheit. You will notice in this particular study, we only used the second and third pump on our applicator. The rates were fairly similar to what they were in the previous study. And again, we got excellent temperature control with the surface with these two rates of propionic acid product compared to the control where we got a lot of evidence of aerobic deterioration. One other interesting thing that happened, and I have no explanation for this right off the top of my head, is that in the control bales of tall fescue, we got a really, really strong response. This is maximum surface temperature over here compared to the meadow fescue and the orchard grass. I can't tell you why, but I thought I'd be obligated to point that out to you. Can't explain that right off the top of my head. Those are fairly similar grasses in terms of their physiology, but that was what happened. Okay, now most of the time when you talk about aerobic deterioration of silages, the primary theory or the conventional theory is that that's usually initiated by yeast. So we did some yeast counts on these bales, on the surface of these bales, as a function of the 3 application treatments with the grasses. And you'll notice that the counts of yeast are 2 orders of magnitude greater. Now this is a log number here, so that's like a factor of 100 greater, which is consistent with the notion that you're improving aerobic stability when you apply this propionic acid-based product. I think it's important to point out that I'm not standing here advocating that you should necessarily do this. It does cost money to do this. I mean, we're probably looking at somewhere between $6 and $12 a bale to put that on at rates in that kind of range. And that may not be something that you want to do. But I think if you are in a situation where you know that you're going to have to expose bales for a period of time, for whatever reason, and it's at a time of the year when aerobic deterioration could be a problem, might be something you want to think about. Please don't consider this a recommendation. Do consider it an additional tool for your toolbox. It might be something you want to do if situation is such that it makes sense to you. Okay, I want to talk a little bit about wet silages. Now, back in the beginning of the presentation, I showed you this graph where we had high moisture baleage represented by this yellow bars. This is pH, and ideal moisture baleage represented by these green bars. And we talked about there's a difference in pH, a more rapid descent with higher moisture, lower final pH, and so forth. It may have occurred to you when I was mentioning that, well, Why don't we just bale them wetter? That would seem logically to make a little bit of sense. There's really three main reasons why that's typically not recommended. And the first two are probably not as important as they once were. The first one is related to safety. You have a 4 by 4 foot round bale in that 60% moisture range that can weigh roughly 1,500 pounds, at least the ones coming out of our baler do. And if you are handling those with an undersized tractor under uneven ground, that's a legitimate safety concern. When I started working with round bale silage at the University of Arkansas, and people had not dealt with this very much, there was a lot of bales that were handled like that with undersized tractors. And if you've ever been to Fayetteville, Arkansas, you know that that's the definition of uneven terrain doesn't even come close to describing some of that. So safety is a concern. Also, the balers themselves. Now, today, most balers do handle wet bales better. You have silage specials that are marketed that way and so forth. But it's important to remember that they do generally handle drier bales better than they do wet ones. I know with our baler, which I said before, I like fine. When we get up about 65% moisture, we start having problems with wrapping, tying, all sorts of things. Occasionally it becomes a little frustrating. So even though equipment design has improved dramatically, you know, these balers are still co-equally designed to bale dry hay. So, you know, the main reason, though, that we do not recommend baling wet silages is the potential for a clostridial fermentation. And in a clostridial fermentation, you have, or a secondary fermentation, usually it does not occur initially. You have Clostridia, which attack free sugars, lactic acid, and protein, and you wind up with production of butyric acid and ammonia. And if the concentrations of that become bad enough, it will significantly affect intake. This is more of a problem and has been researched more thoroughly in Europe, where they typically do not wilt forages. There's a long history of them concentrating on eliminating clostridial products and clostridial fermentations. Because we tend to wilt things, hay crops in this country fairly regularly, it's been less emphasized, but it can be a real problem. What I've plotted here, set this up, this is the butyric acid concentrate, or total fermentation acids, excuse me, in 283 round bale silages from 10 different experiments in Marshfield, Wisconsin. And a couple things here are kind of interesting. Number one, many of these bales were intentionally mismanaged or created in ways you normally wouldn't recommend as part of an experiment. You have to compare the good with the bad in any experiment, so you have to document what the bad is. So there's a lot more variability in this than there might normally be. But when you look at total fermentation acids as a function of barrel moisture, that still explains more than 2/3 of the variability in these bales. What I've also done here is highlighted in this light green the normal recommended range. And in addition to that, the points that are in red are silages that had butyric acid concentrations greater than 0.25%. Now you're going to see, if you do a lot of reading, different recommendations on what an acceptable threshold is. Most people would tell you the acceptable threshold is none or undetectable. You'll see 0.1 in some situations, but this is probably universally going to be more than you'd really like to see. And you'll notice that once you start bumping up against the upper end of this recommended range, you start to pick up more and more of these clostridial products. And one thing about bale silages that's a little bit different, if you think about chopped silages, when you go out across the field, you're blowing that chopped material into a truck, into a wagon of some kind, and there's a certain amount of blending that occurs with that. and then you're discharging that into a blower, or you're dumping it and so forth, and laying it in a bunker, and there's a certain amount of blending that occurs with that. And what you wind up with is a fairly homogeneous product compared to baled silage. Now, with a round baler, at least you're applying whatever occurs and goes into that baler in layers around the outside. So you do have some element of blending. If you're using a square baler, what you bale at this end of the field might be very different from that end of the field. And it does affect the potential for picking up butyric acid products. You can have wide variability, localized spots within those bales where it's much more moist than it would be other places. You can have higher concentrations of legumes, clover or alfalfa compared to grass, and all those things affect the potential for production of clostridial products. Okay, some months ago, I'm sure some of you get hay and forage grower, Mike is here, but they published an article from Dr. Henning at the University of Kentucky where he did some survey work with Kentucky round bale silages. And in that work, he has graphed a very similar thing to what I showed you just previously, but this is actually the concentration of butyric acid here as a function of bale moisture. And these, of course, came, I think, from different farms and so forth. And you'll notice again that there's not a lot of butyric acid until you start getting up to the upper edge of the recommended moisture range. And once you get beyond that, you start picking up clostridial products. In this case, it's measured as butyric acid. So it's always nice when you get the same answer in more than one place. That's always a good thing. Another consideration for clostridial problems is whether or not you've applied manure or dairy slurry, in our case, to these forages as they're growing. This is a common question in our part of the state. You know, it's been a wet fall or a wet spring, or both a wet fall and a wet spring. My lagoon is full. I've got to put this somewhere or it's going to run over, and that creates all kinds of other issues. So can I put it on alfalfa? And in this particular experiment, we had 4 treatments. There was a control where we applied no slurry. We applied it to stubble after the preceding harvest, and then after a 1 and 2 week delay. You know, this kind of a slurry product does have the potential to burn alfalfa back. We're not going to talk about that here, but it does actually have that potential. And our environmental microbiologist, Mark Borkhardt, worked out a qPCR procedure to look at clostridial counts associated with these treatments. And you will notice a couple of things. First, if you don't put any manure on, you have lower counts than if you do. The longer you delay application, the higher the counts get. And after fermentation, represented by the black bars, compared to the pre-ensiled counts, the counts are always higher. Now, if you've got a lot of experience with silage, I don't think any of that really surprises you. And there was not a great production of clostridial products in these silages because we did bale them quite dry. And that is one way to prevent this kind of a problem. However, this does demonstrate a considerable amount of risk. And as Rich Muck, before he retired, would recommend, and also me, based on what I've seen, this might be a really, really good time if you have the capacity to put on a lactic acid producing inoculant. If you've put manure on like that, you might want to consider doing it. And Rich Muck often would recommend when you had a forage that was at risk for Clostridia, you might want to dry it an additional 10 points compared to what you normally would. And that'd be a pretty good hedge against that kind of a problem. I've talked about this, but you might want to know, why we really care about it. What I have here are 2 forages or 2 silages that we produced at Marshfield. And the green bars represent different concentrations of butyric acid in those silages. And these are both pretty high. The red bar represents the concentration of ammonia nitrogen, which is also quite high. Normally, anything above about 10% of the total nitrogen is indicative of a clostridial problem. So these are both, there's clostridial activity in both of these. And what I did was ship these to a former partner in crime at the University of Arkansas, and he ran them through, or had a grad student, Valens, ran these through some gestating sheep. And with the greater concentrations of clostridial products over here, you can see that you get about a 10% depressed intake of both dry matter and organic matter compared to the lower concentration. Please understand that both of those are way too high. So we don't have anything there that's the minimal butyric acid to really compare it against. But this is the kind of problem you can get into, and it's why we're concerned about it, or at least one reason. Okay, the last thing that I want to touch on is dry silages. And this has been a subject of some of our recent work in some ways. I've mentioned Rich Muck. He was the silage guru at the Dairy Forage Research Center for many, many years and retired fairly recently. But he said back about 35 years ago, an implication for management is that fermentation or decreasing pH is relatively unimportant in producing high quality dry silages. And that's kind of interesting because I think the mindset that we all have, and I'm as guilty of this as anyone, is that you want to drive fermentation. And under normal circumstances, that's true. You get stability from a low pH, and that's really important. However, not if the material is dry. Now, of course, Rich made this comment back in an era when there was a lot of oxygen-limiting silos, upright silos around. But my observational trend is that producers, and I would include the managers at the research station in Marshfield, generally are moving toward drier baled silages. And that places increased emphasis on excluding air and probably a lot less on fermentation. All right, let's go back to our 243 round baled silages that we produced from 10 studies at Marshfield. And in this particular case, I've plotted the concentration of lactic acid as a function of bale moisture. What I want you to concentrate on is the cluster within that red circle. You'll notice at these very, very low bale moistures, you get very minimal production of lactic acid, and in many, many cases, you may not even be able to detect it at all. Now, once you get to the recommended range, you start to see an increase in the production of lactic acid, and again, moisture will drive fermentation, so it continues to increase. Again, despite all the variability in conducting these various studies, moisture alone represented about 2/3 of the variability within that relationship. So that's actually quite high, I think. But the key thing to take home here is this does not mean that these bales here were no good, that the quality was no good. They were perfectly excellent quality forage. What it means is you're preserving those bales by excluding air with very little benefit from fermentation. And that poses some interesting things which we'll talk about here as we wrap this up. I thought I would go ahead and throw this in too, because the previous slide probably doesn't represent quite as well what actually happens. I've limited this to 24 round baled grass silages from a single experiment. And basically what I've done is plot the same thing. Concentration of lactic acid is a function of bale moisture. And you'll notice that the curve is a bit more complex. In this case, it's actually a quartic function, which is just a fancy way of saying there's 3 bends in the line, okay? At some point back here, when this material is really dry, you get 0. And then as you get a little bit of moisture, you see an increase and a bit of a plateau until you start to approach this threshold of the recommended range. then the production of lactic acid takes off. And if you extend this out to where it's very wet, which I'll show you in the next slide, this will actually decrease because you're likely to pick up a clostridial response which will metabolize lactic acid. I want to return to Dr. Henning's article in Hay and Forage Grower, and he basically has plotted the same thing here, represented by these green dots. Have concentration of lactic acid, represented by the green dots, as function of bale moisture in his survey study. You will notice very little production up to this initial threshold of the recommended range, then you start to see an increase. Now, in this particular survey study, he had some bales that extended to quite wet, and you'll see that many of them have decreased concentrations of lactic acid because it's been lost to clostridial activity. Okay, the last thing that I really want to touch on before we quit here is related, and it's a common question that we get in central Wisconsin and a concern. And that is, what about situations when I really want to bale dry hay, but I'm just in an environment or a circumstance where I cannot get it dry enough to store properly? And many of you know that as these bale packages get bigger and bigger and bigger, the sensitivity to spontaneous heating in dry hay increases. It becomes a really difficult eye of a needle to thread. So we thought we'd do an experiment to actually look at that a little bit. And in this experiment, which was just published actually this week in Applied Animal Science, we had a 2x2 factorial arrangement of treatments. Bales either received a preservative or they received 7 layers of plastic wrap. So there's actually 4 treatments in there. The moisture content was right in that range where it becomes problematic, at least in Marshfield. We can get things down to 25% pretty easily, but getting them down to 15% is a whole other challenge. So we hit this pretty well in terms of setting it up. Now, this propionic acid-based product was applied at 0.27% of wet bale weight. And that actually is a bit low in this moisture range based on the label. However, this moisture is based on a laboratory determination. The determination made by the applicator on the baler was more like 20%, in which this application rate is on target. Now, normally, in my experience with our baler and our setup in Marshfield, the estimate on the baler and what we get in the laboratory is not that different. This was a fairly unique range. I can't explain why, it just was. But to be fair, I need to point that out. All right, now we measure heating in these bales during storage. And to do that, we used a heating degree day concept, which is similar to a growing degree day concept. You have a threshold, and whatever increment the temperature is above that, you kind of subtract that out and then sum it over the entire storage period. Basically, read this as just a measurement of heat. It's one number that represents how hot that bale got and how long it stayed that way, okay? You'll notice that when I considered all the bales, all of them that were wrapped incurred very, very minimal amount of heating units compared to those that were unwrapped. Now, the unwrapped, of course, would include some that had acid on and some that did not. But these are all highly significantly different, okay? If you look only at the unwrapped bales and compare the preservative versus the control, despite the fact that we may have underapplied this acid just a little bit, there is a significant difference at 30 days and 45 days where we did get some control of heating based on the application of the preservative. We did have a fairly significant differential out at 84 days, which was the extent of the experiment, but that was not statistically significant. If you're to look at dry matter recovery, didn't matter whether they had a preservative or no preservative. If they were wrapped, we recovered after 84 days an extraordinarily high percentage of the dry matter in those bales. And that was not anywhere close to significantly different. However, for the unwrapped bales, we did get improvement in dry matter recovery when we applied the propionic acid-based product. If you want to look at the recovery of energy, what I have here is the energy expressed as net energy of lactation initially for all the bales. For those that were wrapped, there was not a difference there between that and the initial, which means we really, from a statistical standpoint, did not lose any energy as a result of fermentation. However, when they were not wrapped, you see there was quite a loss. Also, these do tend to be different. So anyway, this concept of wrapping bales at a dry level when you're in a position where we're not going to get them dry, it's going to rain, I have to get this off, I'm going to lose it if I don't get it off. I think it holds some promise. Now, we haven't followed up with this, but in an initial trial, it was quite effective. If you extend that a little bit and look at the fermentation in these really dry silages, you'll notice the pH remained pretty high. There's very, very little production of lactic acid or total acids. And also, one thing that happens when you apply a propionic acid-based product during fermentation is you do tend to pick up increased concentrations of alcohols. And that did occur also in this particular experiment. We went ahead and looked at, after exposure, at aerobic stability. And in this particular case, we exposed these bales from early November through early December, middle of December. And during this time period, it was quite cold in Marshfield. And we did not measure any kind of a temperature response between bales that had been wrapped or bales that had preservative or no preservative and so forth. However, when I did go back and look at these yeast counts, you will notice that there's higher yeast counts, at least numerically, when you don't apply the preservative, which is consistent with what we've talked about in past slides. Now, it's important to note, again, this is a log scale. This number here is actually about 4 times as large as this one over here. So that's consistent with what we've seen before, that there is some improvement in aerobic stability when you expose those bales. With that, I'm going to stop and take any questions that you might have. And yes.
Is that limited to silage, or is that something that can, I think you mentioned it in grasses too, is that something that can be done with alfalfa?
Correct me if I'm wrong and I don't understand your question. You were asking whether it made any difference, basically what the forage type was when you applied acid, right? No, you can apply it to any kind of hay crop.
Is it going to be at a different percentage because it was maximized at either 0.44 or 0.8 as far as the benefits of it in the silage in that one chart you had?
The 2 studies that we've done, it would appear that on our applicator, which is the second highest pump in terms of delivery rate, which produced somewhere between, excuse me, 0.4 and 0.5% of wet bale weight, that you got the maximum benefit. To go beyond that, it did not appear that it provided any additional benefit. Okay? Other questions? Yes, sir.
What do you think, speculate, do you think a large square bale that's probably denser would have better aerobic stability when unwrapped than a
I can't speak directly to that, but I think there's a
Repeat
whole
that.
lot of variables in that question.
Repeat the question for the.
Yeah. Mike asked if a large square bale, which he's presuming will be more dense, if that would have better aerobic stability after exposure than a round bale. I can tell you that the yeast and mold counts in the core of a round bale are not as high as they are at the surface. So that kind of speaks to your question, but I know with our operator, well, actually he's in that picture and I need to give him credit. That's the field crew there for the University of Wisconsin. They do a wonderful job. So they're responsible equally for what you've seen. But Scott Fisher is capable of producing very, very high dry matter densities in those round bales, which actually can get up well over 15 pounds of dry matter per cubic foot. So I think it's operator dependent is what I'm trying to tell you.
Is it going to be that high on the outside of that round bale too? Is it going to be that high on the outside of the round bale?
I've only ever measured them exactly on a whole bale basis. I would think not, but those are whole bale measurements.
Any other questions? Well, Wayne will be around for a little bit longer if you'd like to stick around and ask a few questions privately. I do want to say that if you did not get a copy of the handout, there is a copy of the handout over on the desk. And all of these seminars are being recorded and will be placed on the web on a YouTube channel for the World Forage Analysis Super Bowl. And on the back side of this little card that's sitting in a chair over there and also on the table is the link to that. And then you can also pick up another card that has the link to our webinar series for the Dairy Forage Research Center. We do those twice a month on the first and third Wednesday of every month at 3 p.m. Central Time. We conduct those webinars and present research like what Wayne has presented today of what's going on at our center. So with that being said, let's thank Wayne for a great presentation. And thank you all for coming out. We hope you enjoyed it and hope you'll come back next year. Thank you so much.